Okay, this is the Math 220 Linear Algebra final review, and we're looking at problem number 9 in that review packet. Given the following eigenvalues and their corresponding eigenvectors, graph the eigenspaces and indicate the direction of the trajectories for the eigenvectors in the space. So the first thing we need to do is plot those. The eigenvalue 1/2 has a corresponding eigenvector of -2, 5, and the eigenvalue 2 has a corresponding eigenvector of 2, 1. So we plot -2, 5. So -2, 5 would be right about here. There's -2 and up 1, 2, 3, 4, 5. That's that eigenvector. And we know that all corresponding eigenvectors will be multiples of that for that eigenspace, and it will go through 0, 0, of course. Which again, we emphasize 0, 0 is not an eigenvector. It's part of the eigenspace, but it itself is not an eigenvector. So in that eigenvalue, the corresponding eigenvalue for that is equal to 1/2. So that's an attractor. So any eigenvector on here would be equivalent to, when you do a transformation on it, if you apply the matrix to it, it will be half the magnitude of the previous eigenvector. So it would be going to here for the next one. If this was our first one, was 2, 5, then next one would be half of that. And so the trajectory is coming in. It's an attractor. It goes towards the origin. And similarly on this side, even if it's in the negative direction, half of that will be, you'll be cutting those in half. So this is also going towards the origin. So these arrows on the end are indicating that the line goes on to infinity, the eigenspace is infinite, but the attractor goes towards the origin. On the other eigenspace, for lambda equal 2, that is going to be a repeller, and that's of the eigenvector 2, 1. So go over 2 and up 1. There's that first eigenvector right there. And all other eigenvectors, since that's a one-dimensional eigenspace, only one eigenvector for lambda equaling 2, that is a repeller. So every eigenvector will be, when transformed, will be twice as far. Lambda sub 2 is equal to 2. It'll double its length. Okay, so that is part A. Part B is to find z sub 0 if c sub 1 equals 1 and c sub 2 equals -1. Well, we need the general formula for any vector that is being influenced by these eigenspaces is z sub k is equal to, well, you take some constant, it's some multiple, times the eigenvalue for that one to the k power, and then the corresponding eigenvector v sub 1. So this lambda and this eigenvalue and eigenvector correspond, and similarly throughout, if there's a second eigenvalue, then it would be eigenvalue number 2 and its corresponding eigenvector. And if there were more, this general formula goes on and on, actually, depending on how many eigenvalues a matrix might have, so, or a system would have. So anyway, what is z sub 0 then is a little simpler, because if k is 0, then the eigenvalue drops out and you just get c sub 1 times c sub 1 times that vector sub 1 plus c sub 2 times that second eigenvector. And so in this case, it's very simple. C sub 1 is 1, and the eigenvector is -2, 5. So I'll write that this way, -2, 5. And the next eigenvector is -1, next coefficient is -1. And that eigenvector is 2, 1. And so that z sub 0 is going to be 1 times negative 2, 5, or negative 2 minus 2 is negative 4. And then 1 times 5 is 5, minus 1 times 1 would be 4. So there is our first, that's the vector we're going to start with, is negative 4, 4. Now, the following vectors, we can continue to use that formula. And so to find z sub 1, let's put this here, z sub 1 is going to be, z sub 1 still 1, but now we have 1/2 to the first power, so it's times 1/2 times that eigenvector is still negative 2, 5, it's their original eigenvector, and plus, oh, now c sub 2 is a negative 1, so we might as well put minus 1, and then we don't really need to put the 1 there, but this is times 2 to the first power, which is just 2, and that eigenvector, corresponding eigenvector, is 2, 1. So what will that give us? That's going to be 1/2 times negative 2, which is negative 1, and 1/2 times 5, which is 5/2, minus 2 times 2 is 4, 2 times 1 is 2, and so we get negative 1 minus 4 is negative 5, and 5/2 minus 2 is actually negative 5/2, or negative 2.5. I'll write negative 2.5 there. So that's our z sub 1. Z sub 2, it's going to be pretty similar. Let's see if I can do this any more efficiently. Z sub 2 should be 1/2 squared. I don't need to write the c sub 1, it's just 1. That's negative 2, 5, minus 2 squared, 1 times 2 squared, and that's 2, 1. Now, oops, 1/2 squared, that should be 1/4. So negative 2 times 4, well, 1/4, that's negative 1/2. And 1/4 times 5 is 5/4. Minus 4 times 2 is 8, and 4 times 1 is 4. Notice this is always half of this, right, because it's 2 to 1 ratio, so that'll be pretty quick. So this is negative 1/2 minus 8, that's negative 8.5, or negative 8.5. And this is 5/4 minus 4, so that's negative 2.75. Okay, let's try z sub 3. I don't see a quicker way of doing this. This is going to be 1/2 cubed, which is 1/8. So I guess I can just go 1/8 of negative 2 is negative 2/8, or negative 1/4, and 1/8 of 5 is going to be 5/8. So that's a little quicker. And then 4, this is going to be 8, and then 8 times 2 is going to, oh, that's minus. I'll just put the minus through here. That's going to be 8, minus 8, and minus 4 now. Oh, wait. That's 8 times 2 is 16, sorry. Minus 16 and minus 8 there. So that's a negative 1/4 and a negative minus 16. So that's negative 16 1/4. And then 5/8 plus a negative 8, well, that's going to be 7 3/8, so negative 7 3/8 is negative 7.375. And then z sub 4, that's going to be 1/2 to the 4th power, which is a 16th. So it's negative 2/16, or negative 1/8, and 5/16 minus 16 times 2, which is 32, and 16 times 1, which is 16. And so we get negative 32 1/8. That's 125. And then this is going to be 16 minus 5/16. It's going to be 15, and I'll just say that's negative 15 11/16. we're not going to try and plot these perfectly. In fact, this one's probably going to be off our graph. Depends on what we have to do. So we've got negative 4 over 4, and then, so we go negative 4, 4, negative 5 and negative 2.5, negative 8.5 and negative 2.75, negative 16, negative 7, negative 32, negative 15 or 16. So let's go by 4s. Let's draw new eigenspaces for that. So again, those eigenspaces, we've got pretty large negative values. So I'm going to mostly draw this in the negative direction. So I'll orient the grid this way. So we've got negative 2, 5. So if I go negative 2, 5 would be the same as negative 4, 10. So if I go by, if I got to get up to 32, maybe I'll just go by 2s and I'll just get that last one, go through Z sub 3. Should give us a sense of the eigenspace without having to graph Z sub 4 perfectly. So if this is going by 2s, negative 2 and then 5 would be right here. Negative 2, 5, does that look right? Let's plot that fairly accurately. Negative 2 and 5. That should be the same as negative 4, 10. 2, 4, 6, 8, 10 should align with negative 4, 10, which would be right there if I went by 2s. Right here. So here's that eigenspace. This is the 1/2. This is the attractor. This is the one that goes to 0. Okay. Okay. So that's the 1/2 attractor. And then the other one was 2, 1. So that would be 4, 2 if you wanted to go by 2s. So 4, 2 would be right about here. Okay, and that is a repeller. Okay, that's lambda equaling 2. Now if we plot those, what do we get? Negative 4, 4. I'm going by 2, so negative 2, negative 4, 4 would be right here approximately for that first one. Then that was negative 4, 4. Negative 5, negative 2.5. So 2, 4, 5 and negative 2.5 would be right about here. And then negative 8.5 and negative 2.75. Wait. Negative 5 and negative 2.5. Yeah, 5 halves minus 2 is negative 0.5, not negative 2.5. No, it isn't. It's just 0.5. Sorry, that's just 0.5. Correction. It's 2.5 minus 2 is 0.5. So that should be negative 5, and this is going by 2, so 0.5 should be right about here. Negative 2, 4, 5, and negative 0.5, and 0.5 is right about there. That's an errant one. And negative 8.5 and negative 2.75. There's 2, 4, 6, 8. 10 would be there, so negative 8.75 is right about 8.5 is right about here. Negative 2.75 is right about here. And then negative 16, 2, 4, 6, 8, 10, 12, 14, 16, and a quarter, so negative 16.25 is, again, 2, 4, 6, 8, 10, 12, 14, 16. Here's negative 16. Negative 16.25, and then negative 7, so that would be down here, 2, 4, 6, 7, would be right about here. So you can see the trajectory. If I just draw a smooth line, we usually connect those with a line. Now that's, you can see that's going to be asymptotic with that eigenspace corresponding to the repeller lambda equaling 2.